Dear students, welcome to Nivi's Patashala. In this video, we will be studying about deterministic finite automata. Let us see the definition of a deterministic finite automata. It is a finite automata which has determined states to move. The machine moves from one state to another with one input symbol. That is, the machine has only one move for one input symbol. Therefore, it is called a deterministic finite automata. We can determine at which state the machine is going to be with that particular input symbol. The mathematical representation of DFA is similar to the finite automata. It is a phi-tuple representation where we have Q, sigma, delta, Q naught and F, where Q is finite set of states, that is all the states. Sigma is the finite set of input symbols which we also call as alphabet. Delta is the transitions that is happening in the machine. Q naught is the start state and F is the final state, or if we have n number of states. Let us look at an example here. The mathematical representation for this is, we have Q is equal to Q naught Q1, which is nothing but all the states. So here we have Q naught and Q1. Then sigma is the input symbols. We have A and B to be the alphabet, that is nothing but the input symbols. The start state is Q naught and the final state is Q1 because it has two circles here representing the final state. Now this is the transition table we use to represent the diagram. To the first column we have all the states, and in the first row we will be having the input symbols. Here we have a small arrow to represent that Q naught is the start state, and here we have a star or an asterisk to represent that Q1 is the final state. So we can see from the diagram that Q naught on input A moves to Q naught itself. So we have written here Q naught on input A moves to Q naught itself, and Q naught on input B moves to Q1. So Q naught on input B moves to Q1. From Q1 we don't have any transitions happening, so we have represented to be null. Q1 is not moving to any state with A. Q1 is not moving to any state with B. Before we start constructing a deterministic finite automata, let us understand few terms. The input symbols are also called as the alphabets. String is nothing but the sequence of symbols from the alphabet. For example, here we have the alphabet is 0, 1, where strings is nothing but n number of combinations from 0, 1. That is nothing but these are all the subsets from the set 0, 1. Now what is the length of the string? For example, S is equal to 0, 1, 1, 0, 1, which means here I have 5 input symbols. So these are called to be the length of the string is equal to 5. So language is nothing but the set of strings from the alphabet. Now we have n number of combinations we can have from 0 and 1. Taking few of them together is giving us a language that we will be using. Here, what is positive closure and clean closure? Clean closure is nothing but where we have the set starting from epsilon, which means the state can be in final state even without having any transition. But in positive closure, there is no epsilon, which means the state cannot be in final state without any input. So it needs an input to be in final state. Here without any input also the machine can be in final state. Empty language is represented like this, and empty string is represented with brackets with an epsilon in it. Let us see how to construct a DFA where we have substrings of length or a string ending with has some length, then we will use the formula like n plus 1 states. See here we have the alphabet is A, the string is A. So the length of the string is 1, where I will need the minimum states to be n plus 1. So which is nothing but 2 states or nodes. So here I have Q0 and Q1. These are the 2 states where Q0 is the start state and on input A it is going to the final state Q1. Therefore the string is accepted. The string A is accepted as it is in the final state. Here again the alphabet is A and the string is AA, which is having the length 2. So the minimum states I will need is 2 plus 1 state. That is, I will be requiring 3 states. Here I have Q0, Q1 and Q2, where Q0 on the first input symbol A is going to Q1 and Q1 on the second input symbol A is going to Q2. Therefore, AA is in the final state and the string is being accepted. Here I have the alphabet to be A and the string to be A. That is, the length of the string is 3. The minimum states I will require is n plus 1, that is 3 plus 1. So I need 4 states, that is Q0, Q1, Q2 and Q3. Q0 on the first input symbol A goes to Q1. Q1 on the second input symbol A goes to Q2 and Q2 on the third input symbol A goes to Q3, which is the final state. Therefore, the string AAA is being accepted, which means for any substring or string ending with, we will require n plus 1 state. Let us understand the construction of DFA with a simple example. So here I am supposed to construct a DFA with strings ending with AB. So this is the given question. So any string ending with AB is supposed to be accepted by the DFA. Let us see few accepting strings and few rejecting strings. This way we can understand the DFA better. So the minimum string is to be AB. So if I have AB as my string, it is supposed to be accepted. If I have n number of B's ending with AB, still the string should be accepted. If I have n number of A's ending with AB, the string should be accepted. If I have n number of A's and B's, but the strings are ending with AB, then all these strings are supposed to be accepted by the DFA. What are the strings that the DFA should reject? If I only have A, or if I only have B, or if I have n number of only A's or n number of only B's, or if I have combination of A's and B's where it does not end with AB, then these are the strings that the DFA should reject. With this example, string ending with AB, we can know that the alphabet is A, B. That is, the input symbols we have here is A, B and the string is AB. That is, here we have ending with AB. So the minimum string is AB and the length of the string is 2, which means we are having 2 plus 1 state. So length of the string plus 1 is equal to 3 state. So here ending with substring of length n. So any string ending with substring of length n, we will require minimum n plus 1 state. So here I have AB, that is length is 2. So I need 2 plus 1, minimum of 3 states. So the minimum string is AB, that is, here we can see accepting strings. Minimum string is AB, which is supposed to be accepted. So first let us draw a skeleton DFA for AB. So here I have a start state, that is Q0. Q0 on input A goes to Q1 and Q1 on input B goes to Q2. Therefore, AB is being accepted. So here I have 3 states. The length of the string is 2 and I have 3 states, 1, 2 and 3 states. Now let us construct the DFA for this. So we have Q0, Q1, Q2. Assuming that if I have B, B, B and n number of B's ending with AB. So here A and B is going to the final state. Now I have n number of B's. So I am looping B here. So the string is starting with n number of B's. So I am looping B to Q0 itself. If I have B, A, B, then it is B, A, B. It is a accepting string. If I have n number of B's A and AB, n number of B's and then ending with AB is a accepting string. Next, if I have n number of A's and ending with AB. So what I will do, if I have n number of A's and ending with AB, the first A comes from Q0 to Q1 and then all the n number of A's gets looped in Q1 and ending with AB. The last A also gets looped in Q1 and B goes to the final state. Now if you are wondering why can't I loop A here or why can't I loop B here? Now Q0 on input A is going to Q1. Now if I loop A here, if I in place of B if I have A, if I loop A here, then the state goes into a confusion state whether it has to pass A to Q1 or whether it has to hold back A to itself, which means if I have, for example, let us take if I have looped B here and the Q1 state is supposed to give B to Q2, and if I loop B here, then Q1 gets confused whether it has to go to the next state or it has to loop that input B to itself. So to avoid this, we will make sure that whatever it is looping, it does not give. So if Q0 is looping B to itself, then it is giving A. If Q1 is looping A to itself, then it is giving B. Why we call this as a DFA? Because at one instance of time for one input, it can move to only one state. So if I have A here and A here, at that moment of time, it is going into two transition states, which is not possible in a DFA. Next, if I have n number of A, B or B, A and then ending with A, B. So if I have n number of B's and ending with A, B, and then again if I have any other input after AB, if I have any other input, then rather than taking a new state, I can loop back that input to Q1. Now if I have A, B, A, it is supposed to be a rejecting string. See here I have A, B, A. This is supposed to be a rejecting string. So instead of taking a new state for A, I can give back A to Q1 because here we have already looped Q1 to have A's. So it is easy for us to give back A to Q1. Now if I get A, B, A, B, A, B, A, B is again in the final state. The same way if I get A, B and B. So that time I am giving B back to Q0. Q0 is looping B. So it is easier to connect Q2 giving B to Q0. So if I have A, B and n number of B's, then all the B's gets looped in Q0. If I have A, B, A, B, then I will be going from Q0 to Q1, then from Q1 to Q2. Here we have got AB, then again if I have A, then I will get Q1, and if I have B, I will again go to Q2. So it is a accepting string. If I have A, B, B, A, B, so I have two B's in between, I will be having A, B, and B goes back to Q0 and n number of B's gets looped here until and unless it ends with AB. So therefore this state is not required. So this is our completed DFA for string ending with AB. The basic steps to follow while designing a DFA. The first step is to identify the minimum string, And the second step is to identify the alphabets, which means the input symbols. What are the input symbols used in that DFA? Then the third step is to design a skeleton DFA for the minimum string. Whatever we have the minimum string, for that we have to first design a skeleton DFA. And step 4 is to find out all the transitions that can happen in the DFA. And step 5 is to completely construct the DFA. Here let us take another example. Construct a DFA to accept the string B. Here we have only B to B are input string. So first thing is to identify minimum string is B. So the minimum string itself is B, and to identify the alphabet, that the input symbol here, there is no A in the question, so it is only B. So the input symbol is only B. Then we are supposed to construct the skeleton DFA. From Q0 to Q1, B is going from Q0 to Q1, where Q1 is the final state and Q0 is the start state. Then the transition, that is Q0 on input B is going to Q1. So this is how we are supposed to write delta, open a bracket, Q0 comma B close the bracket is equal to Q1, which means Q0 on input B is going to Q1. Construct the DFA and represent in mathematical format. So this itself is our final DFA. The skeleton itself is the final DFA, because here it does not say construct DFA to accept string ending with or anything like that. So only B is the input symbol, and the mathematical representation is Q, sigma, delta, Q0 and F, where Q is all the states, that is Q0 and Q1. The input is B, Q0 is the start state and Q1 is the final state, and the transition table here we have Q0 on input B is going to Q1 and Q1 on input B has no transitions. Let us take another example here. Construct a DFA to accept strings of B's having at least one B, which means 1B is the minimum string, it has to be accepted. 2B's should be accepted, 3B should be accepted, n number of B's should be accepted. So the first step is to identify the minimum string, that is 1B. And the alphabets we have here is B alone. There is no A or any other alphabet in the question. So the only input symbol here we have is B. The skeleton for this input symbol B is from Q0 to Q1. The minimum string is B, so it has been accepted. Q0 on input B is going to Q1, which is the final state. And this is the transition, that is Q0 on input B is going to Q1. Construct a DFA and represent in mathematical format. So here, this is how we can complete the DFA. Q0 on one single input B is going to Q1, and after that n number of B's is being looped to Q1 itself, which means all those are in final state. So for the transition to go to the final state, it requires at least minimum 1 B. After that, n number of B's are still in the final state. So here again we can write down the transition on Q1 with input B. It is being looped to Q1 itself. So Q1 on input B stays in Q1. The table here is we have Q0, Q1, where this is the start state, this is the final state. Q0 on input B is going to Q1, that is Q0 on input B is going to Q1, and Q1 on input B is again in Q1 itself. So Q1 on input B is in Q1 itself. The way to represent in mathematical format, we have Q representing all the states, and the input, that is the alphabet, is B. Q0 is the start state and the final state is Q1, and the transition here we have shown the transitions and also the transition table. Let us look at another example here. Construct a DFA for strings that end with 1, 0. So we have strings ending with 1, 0. So the accepting strings, the minimum string is 1, 0 and 1, 1, 0, 0, 1, 0, n number of ones and zeros ending with 1, 0, or combination of n number of ones and zeros that end with 1, 0. So these are all the accepting strings which are ending with 1, 0. What are the rejecting strings? Only 0 or only 1 or 0, 1 or n number of combinations of zeros and ones which are either ending with 1 or ending with 1, 1 or not ending with 1, 0. So these are all the strings that are not ending with 1, 0. See here we have 1, 0, then again we have 1. So which means 1, 0, these two will end in final state, but again because we have 1, this string is supposed to get rejected. So the way we construct our DFA, we should make sure that the strings that are supposed to be rejected does not get accepted. Here also we have 0, 1, 0, again I have 1. So here 0, 1, 0 itself is to be accepted, but because I have another ending with 1, then this string is supposed to be rejected. So the first step is to identify the minimum string. The minimum string is 1, 0. Second step is to identify the alphabets, that is the input symbols. So from the question we can see the input symbols are 1 and 0. So the skeleton for the minimum string should be first drawn. So 1, 0 should be accepted. So I have n plus 1 state. So minimum string is 1, 0. So that is 2 states and plus 1 state. So 2 plus 1 state, that is I have 3 states, Q0, Q1 and Q2, where Q0 on 1 goes to Q1 and Q1 on 0 goes to Q2. So therefore 1, 0 is being accepted. Now the transition for this 1, 0 should be written here. Delta Q0 on input 1 goes to Q1. So Q0 on input 1 goes to Q1. Q1 on input 0 goes to Q2. Q1 on input 0 goes to Q2. Write down the transitions only for the minimum string first. Later on, as we construct the DFA, we can complete the transitions. So this is the transition table where we know that Q0 on 1 goes to Q1 and Q1 on 0 goes to Q2. Q0 on 1 goes to Q1 and Q1 on 0 goes to Q2. You can see that even in the transition, and we don't know the rest of the transitions which are happening. So we have left it idle to fill it later. So our fifth step is to construct the complete DFA and represent it in a mathematical format. So here we know that these are the strings that are to be accepted. So now consider if I have n number of zeros followed by ending with 1, 0. So I am going to loop those zeros to Q0. So n number of zeros gets looped in Q0 and 1, 0 is going to the final state. Now if I have n number of ones ending with 1, 0, then I can loop ones in Q1. So I have 1, n number of ones and ending with 0. So this is also in the final state, which means the first one is going from Q0 to Q1 and the rest of the ones gets looped in Q1 ending with 0 goes to Q2. Now if I have any number of combinations of ones and zeros and ending with 1, 0 is going to the final state. See here Q0 with n number of zeros and 1, 0 goes to final state and n number of ones and 0 goes to final state. So let us fill the table here, simultaneously filling the tables. Next, here from Q2, after reaching the final state, if I have 1, 0, 0, then it is supposed to get rejected. So I have from here, from Q0, 1, 0 and from Q2, 0 is coming to Q0, which is a non-final state. Therefore, the string is said to be rejected. The same way, I can also have from Q2 n number of ones back to Q1. The trick to understand here is from Q0 on 1, if it is going to Q1, then there is a transition happening here. So from Q0 on 1 is going to Q1. So it is easier for me to loop zeros here, which means Q0 on n number of zeros will be in Q0 itself, and when the input symbol changes to 1, the state is also moving from one state to another state. Here also we know that from the skeleton diagram, from Q1 on input 0 it goes to Q2. So I can loop n number of ones here, because on n number of ones and ending with 0, it is again going to Q2. The same way from Q2, because Q1 is a state looping ones, I can give all the ones to Q1, and because Q0 is a state that is looping zeros, from Q2 I can give all the zeros to Q0. So the mathematical representation and the transitions is given here. So this is the mathematical representation where all the states are Q0, Q1 and Q2. Input symbol is 0 and 1. The start state is Q0 and the final state is Q2. So these are the transitions we have from the transition table. Now let us take an example here. To check the strings 0010110 is accepted or rejected. It is ending with 10, therefore it is supposed to be accepted because we know that 10 is ending in the final state. So on the first 0, Q0 on first 0 loops to itself, and again Q0 on the second 0 loops to itself. When Q0 receives 1, it is moving to state Q1. Now Q1, when it receives 0, it is moving to state Q2. Now from Q2 I again have 1. Therefore it is supposed to be in rejecting state. Therefore that is a non-final state. So from Q2 1 is going back to Q1. Again from Q1 I have 1 which is looping to itself Q1, and from Q1 I have 0, which means 10 is supposed to get accepted. Therefore from Q1 I am going to Q2 on 0. Thank you for watching, and don't forget to like, share and subscribe.